Now that we've talked about how to do the technique of separation of variables, let's actually apply it to a couple problems. We're going to start by solving the differential equation. X squared times y prime is equal to x plus 1 times y. So first couple things that I'd like to do here. First thing I'd like to do is express y prime as the implied dy over dx. This will allow us to figure out which side we want the appropriate variables to be on. Now, as I demonstrated in the last video, first thing I'm going to do is multiply both sides of the equation by dx. This will effectively cancel out the dx's on the left-hand side, leaving us with the following expression. X squared times dy is equal to x plus 1 times y times dx. This means I want to gather all of the y terms on the left-hand side and gather all of the x terms on the right-hand side. I can gather the y terms on the left side by dividing both sides by y to get the y away from the right-hand side. And I can gather the x squareds on the right side by dividing both sides by x squared. This leaves me with the following equation. This will be dy over y is equal to x plus 1 over x squared times dx. In this form, it appears ready to be integrated, so I'm going to integrate both sides with respect to the appropriate variables. Left-hand side is going to be relatively straightforward. This will simply be the natural log of the absolute value of y. On the right-hand side, before I integrate, I'm going to distribute the x squared to both of the terms and call this x over x squared plus 1 over x squared, so that we will be integrating 1 over x plus 1 over x squared. That integration is going to give us the natural log of the absolute value of x, and according to the power rule, thinking of this as x to the negative 2 power, this will give us negative x to the negative 1 power. And as I mentioned in the previous video, we will only need a singular plus c associated with this. Next step that I'm going to do is actually solve this for y, and the way that we can do so is by exponentiating both sides. So we'll raise e to the power of both sides. On the left-hand side, this will give me the absolute value of y, and on the right-hand side, this will give me e raised to the power of natural log of the absolute value of y minus 1 over x plus c. Using the property of exponents, I can split this into e raised to the power of the natural log of the absolute value of x times e raised to the negative 1 over x times e raised to the c power. Now, c is just a generic constant of integration, and e raised to the power of c would be just another generic constant. So I'm going to let capital A represent e raised to the c power. That allows me to state that the absolute value of y is going to be equal to, simplifying each of these, the absolute value of x multiplied by e to the negative 1 over x power multiplied by a. A seems like a coefficient, so I'll put that up front. Based on how this was defined, it's impossible for a to be negative, as it is the output of an exponential. So to get rid of the absolute value bars, I would simply take away the fact that a must be a positive value. So with that in mind, we can give a final answer of y is equal to a times the absolute value of x times e to the negative 1 over x power. That'll be good for a final answer. And again, taking away the absolute value bars simply means that a could potentially be positive or it could potentially be negative. I guess it technically could be 0, but then this would be a really boring problem. Let's see if we can replicate this process one more time with one more example problem. See if I can scrounge one up. Oh, there it is. Y prime is equal to e to the x times e to the y. So, first things first on this one, like we did for the previous problem, I'd like to refer to y prime as dy over dx. Then we'll start with the same separation of variables as what we did for the previous problem. Multiply both sides by dx. On the left-hand side, we'll have dy is equal to, on the right-hand side, e to the x times e to the y times dx. The implied positions of the dy and the dx means that we should gather all of the y's on the left-hand side, and gather all the x's on the right-hand side. We can accomplish this by saying, let's multiply both sides of the equation by e to the negative y, or simply divide by e to the y. However, in this form, it'll be a little bit more apparent as to how to integrate this. That's dy. Tried to write dx. That's wrong. dx goes over here. In this form, we're now ready to integrate. The left-hand side would be a simple u substitution. We would wind up with negative e to the negative y. And on the right-hand side, antiderivative of e to the x is simply going to be e to the x. We'll also tag on the plus c now that the integration is done. To finish solving for y, we first multiply both sides by negative 1. Now when we multiply both sides by negative 1, it technically will turn your generic constant into a minus c. However, because it's a generic constant, it doesn't matter if we're saying add it or subtract it, so no big deal there. Then apply a natural log to both sides. That's the natural log of negative e to the x minus c. And then multiply both sides by negative 1. We wind up with y is equal to the negative natural log of negative e to the x minus c. Now actually I think that we can verify that this means that c has to be a negative value. Actually we probably could have back up here because e to the x is positive and negative e to the negative y is negative, so c would have to be some negative constant in this case in order for this to even make sense. So c has to be less than 0. Not 100% necessary when you're solving for this, but just a nice thing to point out. We'll call that a little bit of bonus math.